Today we will study how to translate a assembly language program to equivalent machine language program manually. So we have a assembly language program. So this is the assembly language program we have. We will translate this assembly language program to the equivalent machine language program. So let us start from the first statement of the assembly language program. So the first statement is start 102. That means it means that they start the program from the address 102. So that means the the address of the first instruction will be 102. Address of the first instruction means address of the first instruction of the machine code will be 102. So the next instruction is read n. So read n, you can see what is a read n. Read n is a your assembly language statement. So read is the machine of code and n is the operand. So read has a machine equivalent 09. So read is a mnemonic of code. So mnemonic of code, each and every mnemonic of code has a machine value. That means you can say it has a mnemonic address of the instruction. The mnemonic address of the instruction is 09. So here this value is obtained from the mnemonic table. So n is a nothing but an identifier or a symbol whose address is not known. So we have written 0. 0 means the register operand. If since there is no register operand in this instruction, so it is 0 here. So you can see the format of a machine language was like this. So we have already studied earlier in our class that the format of a machine language is sign will be plus and minus, plus or minus. So here we will consider plus sign only for assembly statement. We'll later on we will know when minus is written in the sign when we will study your macros. So opcode, in opcode there are 2 digits value. Register operand is a 1 digit machine. In the machine instruction there is 1 digit for register operand value and 3 digits are used for memory operand or the address of the memory operand. So let us come to the program again. So read n, since there is no register operand, B register, C register, so the register operand part is 0. Then n, value of n means the address of n initially is, you have to keep it blank. 115 I have written, but it will be taken from a later declaration. So you can say that this n is called forward reference. That means it has been used before it is declared. So the assembler does not know the address of n yet. So initially it is kept blank. When you translate the machine instructions, this whole part you have to keep blank. We'll put the value later on. So let us now leave this 115 value. Let us move to the next instruction. Move bar will have the move bar B register 1 has a address, machine address is 103. So move bar has a opcode value, machine equivalent machine opcode value 04. B register has a value 2. 1 is now left blank. So in this way we will put all the values. So now if we come to this instruction, then again, what is again? Again is nothing but a level of the level of this instruction. So level of this instruction is again. So mult is a multiplication. So multiplication has a machine equivalent value 03 and B register is 2. Term is now kept blank. 118 will come to later. So in this way, when we assign addresses to each and every instruction, so suppose you can see that this is the instruction, it has a 106 address, then this instruction 107, this next instruction 108, next instruction 109, next instruction 110, next instruction 111, 112, 113, 114. The program is stopped. Now we will declare some constants or and also declare some the storage locations of some memory variables. Okay, so n is the name of the symbol or the the variable or the symbol or variable or identifier, and ds means declare storage. So it is nothing but declarative statements. So we know that there are 3 types of assembly statements are there. One is your imperative statement, one is assembler directive, one is declarative statement. So this is a declarative statement DS. 1 means 1 byte of memory will be allocated for the uh, symbol n or the identifier n. So and it has the address 115 now. Now we got the address of 115. Now we'll put the value of 115 where n was there in the instruction. So here you can see read n, 09 for read. There is no register operand, so it is 0. The value now, the address of n is now found from here 115. Now the 115 is will be put in this here 115. So similarly the another n is there in this instruction. So 115, see, you can see 115 has been has been put here. It has been put here. So now in this way the address of the other instruction, that means declarative statements, has been calculated. So as a result since it is 1 byte of instruction, so next address of the next declarative statement will be 116. If we have written 2, that means declare storage 2, then it will be 117, not 116, because 2 consecutive memory locations are allocated. Then the next address of the next instruction will be allocated. So if I write 2 here, then 115, then 116, then 117, the address it will be 117. If I write 3 here, then it will be 118. The address of this instruction will be 118. So the declare storage for the result, that means the address of the result will be 118 in that case. So similarly the other instructions, that means the other addresses are also calculated. So here this is a calculator, and these values are put where required, where it is there. So you can see that the address of 1 has been put 117, address of term has been put 118. So this is, in this way the machine code is written. So now we will see what is the declarative statements are generally in 2 types, and some other types are also there depending on the architecture of the microprocessor. So you can see DS, declare storage constant, and label is also given, and DC means declare constant and a value, and label is also should be given. So because label means the symbol level. So here you can see here it is label, these are labels, and result 1, term 2, these are labels, and DS, DCs are written here, and the number of bytes or the value of the constant is written here. So this for DC 1 is a constant, that is why it is written in single quote. So again one constant 2 has been declared, the name of this constant is TWO is written here. Okay, you can give any other name also. I can write Raz here, declare constant, say 7. Okay, so this is it. So let us now move to the design specification of an assembler. So design specification of assembler, the first step to design the first specification is to identify the information necessary to perform the task. Number 2, design a suitable data structure to record the information. Number 3, determine the processing necessary to obtain and maintain the information, and determine the processing necessary to perform the task. So what are these things? So identify the information necessary to perform the task. So what are the information that are needed to translate a assembly code to a machine code? We need a database where the addresses of your mnemonics, or the symbolic addresses, that the symbolic, that means the operand, that means you can say that the mnemonics has some machine equivalent values. So these values should be stored somewhere. The design next is design a suitable data structure to record the information. So what are the other information that should be recorded? The other information are nothing but the symbol address of the symbols, that means the address of the constants or the address of the variables that should be stored. So we have to build a table, suitable table. Data table is nothing but also a data structure. Okay, number 3, determine the processing necessary to obtain and maintain the information. So processing means we need a data structure called LC, or location counter, where which is needed to build this table. That means the location counter points to the address of the next instruction to be processed. So this is determined and necessary. So we need another data structure called LC, or location counter. Okay, next comes your determine the processing necessary to perform the task. We have to progress the location counter to find the addresses or calculate the addresses of the instructions. Okay, so let us see. So we have in a two-phase assembler. In a assembler generally there are 2 phases, or it may be in 1 phase also. So let us see in a analysis phase what happens. the analysis space, in the analysis space, source program is given to the analysis space. The analysis space, in the analysis space, symbol table is built. So symbol table is built. That means the symbol table contains two fields. One is name of the symbol and the address of the symbol. Okay, and another data structure is there. It is called mnemonic table. Mnemonic table contains three fields. One is name of the mnemonic, then the opcode, mnemonic opcode value, and the length. Okay, length means how many bytes are necessary for this session. So add, in case of add, we will write 0 1. So you can see here, come here, add, here add is there, the value of add is 0 1. Okay, from where this 0 1 has been put here, it is been put from the mnemonic table. Okay, now this mnemonic, who builds the mnemonic table? So mnemonic table is generally is a pre-built table. That means it is already there with the assembler. That means that when the assembler is built, the mnemonic table are already been given to the assembler. Okay, so it depends on the architecture. Different microprocessors have different sets of your addresses. So 8086 is a 16-bit microprocessor. It has more addresses than 8085 is a 8-bit microprocessor. It has different set of your mnemonics. So this mnemonics table will be different for different architectures and processors. So this is a pre-built data structure. It is already there with the assembler, and this symbol table is built dynamically depending on the program you are writing. Okay, so this you can see the analysis space builds these symbol tables, and this symbol table is used in the synthesis space in the next in the synthesis space. Okay, and these mnemonic tables are used both by analysis space and the synthesis space only used. Okay, so that is why arrow is in this direction. Okay, when the arrow is to the data structure or towards the table, that means it is writing something to this symbol table. So to this data structure. So you can see that analysis space arrow is here in this direction. Arrow is in this direction. That means analysis space builds this, writes this symbols and the addresses. Okay, and dot means your control transfer. Okay, when the symbol table will be built, the control will be transferred from analysis space to synthesis space, and the synthesis space will generate the target program. Okay, that means this the values which are not been missing in the first your analysis space, it will be put 115 is will be put in the synthesis space. Okay, like this. So let us come to the tasks performed in the analysis space. In the task performed, the first task is to isolate the labels, mnemonic opcode, and the operand fields of a statement. Number 2, if a label is present, enter the pair symbol LC counter. That means the address of the location counter is placed. So symbol means here this symbol again is a symbol, n is a symbol or a variable, or you can say it is a identifier. Okay, so the address of this symbol again is 104. So how this 104 comes? 104 comes from the location counter value. That means the value of the location counter. So when the location counter comes into say this statement, so it will be 104. Before coming to this statement, the location counter value is 104. So it is been put here. That means again is been assigned 104. That means 104. Okay, so that means again contains after this address. Okay, 104 address. Similarly, n is 113. Okay, 113, or I think it is your it is 114. It will be 114. 114. It will be here 114 because it is n 114. And 104 is I think again is 104. Okay, fine. So this is calculated from the location counter value. Okay, so let us now come to the okay. So this is the task performed in the analysis space, and I think one thing is there, 104 again value is 104. Okay, so I think again value here it will be 105. In our case it is 105. Okay, and the value of n is 115, not 114. It will be 115. 115. It will be 115. Okay, fine. Because value of n is 115. Okay, and the again is 105. Address of again is 105. Okay, now it's clear. The LC, actually LC contains the address of the instruction, so the address of the instruction is put here. Okay, fine. So next comes tasks performed by the analysis phase. Isolate the label, mnemonic opcode and operand fields. We know the next if a label is present, the enter the pair this into the new entry of the symbol table. As I have already told, check the validity of the mnemonic opcode through the lookup in the mnemonic table. That means check whether the mnemonic opcode has been correct or not. So if I write in case of add, if I write dead, then there is no entry in the mnemonic table for dead. So that will be an invalid mnemonic opcode. So that is why I have written that check the validity of the mnemonic opcode through the lookup in the mnemonic table. Lookup means checking in the mnemonic table whether the mnemonic opcode exists or not. Okay. So if it does not exist, then it will say that you have misspelled or you have written a wrong mnemonic opcode, which is not a valid mnemonic opcode for the assembly program or the assembly for the assembler. So next, number 4 is perform the LC processing, that is update the value contained in the LC location counter. LC means location counter, by considering the opcode and operand of the statement. Okay, so perform LC processing means progress the location counter. Then what is the task performed in the synthesis phase? Obtain the machine opcode corresponding to the mnemonic form of the machine from the mnemonic table. Obtain the machine opcode, as I have told you, they obtain the machine opcode. That means the machine opcode for the mnemonic add is 01. So it is opcode from the mnemonic table. Obtain the address of a memory operand from the symbol table. Obtain the address of say n is 115. Address of again is 105. So take these two values and build the machine code. So here if you see that the mult, okay, the mult is a multiplication mnemonic opcode. So mnemonic, and its opcode value is 03, which is obtained from the mnemonic table, and B register, its value is also obtained from the mnemonic table. The 2, and term, the term value is obtained from the symbol table. The address of term is 118. So all these values are put together to build the machine instruction, and this is done by the synthesis phase. Okay, so that is why obtain the address of a mnemonic obtain the address of a memory operand from the symbol table. Obtain the machine opcode corresponding to the mnemonic from the mnemonic table. Then last one, synthesize a machine instruction. That means create machine language statement. If necessary, put the address of the symbol, variable or constants in the machine language statement. Okay, so this is all about your synthesis phase. So one thing I need to mention you that in a 2-pass assembler, the symbol table is built in the first pass, and it is in the second pass the symbols are used or put in the actually in the blank, that means in the machine instructions. So in the first pass it will leave it blank, and it will read the whole program, and it will record all the addresses of the symbols in a symbol table. Okay, then in the second pass it will put the value the addresses of the symbols in the machine instructions. So there are 2 pass. In case of single pass assembler, what happens in the single pass, you have to put the addresses. How will you do that? So in the single pass, one data structure called table of incomplete instructions is created. That means that is what this is also another data structure. Okay, so data structure means it is a table data structure. So it contains 2 fields: the instruction address and the symbol, where the symbol 1 occurs. So you can see the symbol 1 occurs say in this address, symbol 1 also occurs in this address. So see this where the 1 occurs, the addresses where the 1 occurs are recorded in the table of incomplete instruction, and the value, the actual machine or address or the actual memory address of the symbol is left blank. So from the when the whole reading of the whole assembly language will be completed, it will find the addresses of the symbols. Okay, and when the addresses of the symbols will be found from the table of incomplete instruction, it can say that 1 occurs in those locations. So those values will be those, that means the addresses of 1 will be placed in those locations. So this is the task done in a 1-pass assembler. So the forward references, that means the value of the symbols, which is the address of the symbols which are not been calculated yet, are called forward addresses. So that means the symbols where it is used before its declaration is called your forward reference. So forward reference is handled in 1-pass assembler by using a technique called backpatching. That means what? It creates a data structure called TII, that means table of incomplete instructions, where it records the symbols, that means whose addresses are not been calculated yet. Okay, and when the whole pass is completed, it will find the addresses of the symbols, and the addresses of the symbols will be put where from the TII in the locations where it occurs. So this is the this technique, backpatching technique, used in 1-pass assembler. Okay, so I think you got these things, and if you have any question, then ask me. Thank you.